absorption going from down to up, sigma plus, and that's associated with the positive frequency component, e to the minus I omega t. And then we have emission going from spin down to spin up, and that is the conjugate here. Okay? And that Hamiltonian, as all Hamiltonia are, that's not really plural, I just made that up. For spin, no, that's not the operator, this is equivalent to the spin in a magnetic field. Just for convenience, because I took spin up to be the higher energy state, took the gyromagnetic ratio to be negative, like an electron. Doesn't really matter, we could have done it the other way around. Just too many minus signs to keep track of. Is equivalent to spin in a magnetic field, which has a static component along the z-axis, what we're calling the quantization axis, and then a magnetic field in the transverse plane that is rotating around it as a circle, in a circle, okay? With frequency omega. So this problem, this quantum problem, maps onto this gyroscope-like problem where there is a static magnetic field along the z-axis and a rotating magnetic field in the xy plane. And that is the problem of spin resonance, magnetic spin resonance. So when the rotating field frequency matches the free Larmor precession around the z-axis, then this thing will Larmor precess around the transverse field at this frequency, capital omega, which we call the Rabi frequency. Okay? So that's what's going on, and we can look at this in terms of the full quantum dynamics now by, first of all, turning this time-dependent problem into a time-independent problem. And then we can solve it exactly. And so the way we made it a time-independent problem is that we went into the frame rotating around the z-axis at the drive frequency. It's not quite the interaction picture, but it's like it. The interaction picture, you go into a frame that is rotating at the dynamics of the free evolution, which would be omega naught. Okay? But it's in the similar spirit. And in the rotating frame, the effective Hamiltonian we found then looked like this, where delta is the difference between the drive and the resonance frequency. It's known as the detuning. Okay. All right. So with that, we can, if we have the time, effectively time-independent Hamiltonian, well then the time evolution we can write down explicitly. Because we could just exponentiate that Hamiltonian without worrying about time-ordered exponentials or any of the challenges associated with time-dependent Hamiltonia. And this is my time evolution operator then, okay? So it is the rotation of the spin around an axis that depends on the detuning and the Rabi frequency. It precesses about that axis at this frequency. Okay? So when we are right on resonance, so if we take the state at time equals 0 to be spin down, for example, then if we draw a picture here, this is the block sphere. If I start spin down, if I'm right on resonance, then this is being torqued in the rotating frame about the x-axis. Let's call the x-axis here. This is the y-axis. This is the z-axis. Right? And so if I'm right on resonance, then I'm talking about this axis, right? And I will then process about that axis going all the way from spin down to spin up at a frequency omega, right? And the solution in that case, the probability for going from spin down to spin up as a function of time is this, which in this case is sine squared the Rabi frequency over 2, right? Which are 1 minus cos over 2. So that this, on resonance, this probability oscillated like a sine squared from 0 to 1. Okay? With a Rabi free, it's supposed to look like, I'm sorry, but it's supposed to look like a sine squared, and this is t equals 2 pi over t. This is pi over t. This is pi over 2t. And as we discussed, oh, I do this backwards. Sorry. I'm rotating around the x-axis. Okay, I just drew it, not the y-axis. Let's just. So my torques are along this direction. That I do this, then this guy will precess around this circle, right? So that at time, when the time here is equal to when omega t is equal to pi over 2, I'm along this axis, and when omega t is equal to pi, I'm here, etc. Okay, so the spin is precessing around the x-axis from spin down to spin up. Yeah.
So, okay, so the time evolution operator goes to this exponentiated sigma operator in the n direction. Is that correct? So that acts on the state. It rotates the state, and then it gives it some phase.
Well, it does what it does. So, this operator, as written, we know that we can express it in terms of a combination of the identity and the Pauli matrices by the formula that we all remember for SU2. Okay, so that is the time evolution operator.
Okay, I guess that those states are not eigenstates of the sigma n, or
no, they are not.
They're not, because they get changed by it.
Indeed.
Okay.
Right? I mean, if, of course, I started the system along, in this case, the x-axis, it wouldn't do anything to it. It would give it a phase.
Okay.
So when this operator acts, on this state, on, say, spin down, this is equal to this minus I sigma over 2. And then I have sigma n over here, which would be minus delta over omega spin down plus spin up. That's what happens when you apply sigma n. Sigma n, I'm sorry, this is backwards. This is along the z, this is along the x. Right? So it makes that superposition. Now when delta equals 0, this is equal to...
Isn't delta be a minus delta?
No, because it's big down. But let's not worry about these tiny minus signs. That's not the important conceptual things or the important things. We have that. So that state, for example, when omega t was pi over 2, this was cosine of pi over 4, which is, so when at t equals, when omega t was pi over 4, this is equal to 1 over root 2 spin down minus I, oh gosh, it should be up. That's not a d10. And 1 over root 2 spin up, or equivalently minus I spin up plus I over root 2. So that state is spin down along y, which is what we expect. Right.
What happens with the omega omega delta?
When delta is 0, which is the case I'm considering right now. I'm sorry, Rich, what are you asking?
The delta omega or omega tilde?
When delta is 0, omega tilde equals omega. So this becomes 1. So when I'm right on resonance, I rotate, I go all the way from spin down to spin up, right? That's because, I mean, the reason it evolves is that my system didn't start in an eigenstate of the Hamiltonian, right? If I'm off resonance, when delta is not equal to 0, then I have a component of the torque that's along the z-axis, right? So my torque vector, say for a positive delta, would look like that in that case. And the way I've drawn this now, this guy would process around that axis. Well, it's supposed to be a circle. So it processes around that axis. And in that case, my probability to go from down to up as a function of time would look like omega squared over omega tilde squared sine squared omega tilde t over 2. Okay? Or omega squared over omega squared plus delta squared sine squared. So in that case, what we find is that the system doesn't go all the way to from spin down to spin up, but and we can see that, and the bigger delta is, the smaller this circle, right? I mean, if delta was huge compared to the Rabi frequency, then I would barely get out of the ground state at all. Yeah?
Could we have done this with Barry's phase?
Could we have done this with Barry's phase? I don't see that, it's not quite the same thing. Various phase is about adiabatic changes. This is a time independent Hamiltonian, it's just time dynamics. Really see the connection here. It does look, in some sense, it looks like solid angles and such, but I don't think there's that connection in this case. Right. So, this is what we call Rabi oscillations, or sometimes known as Rabi flopping. That is to say, if I go back over here, if I let's say I'm right on resonance, if I drive the system, it will flop back and forth, or oscillate back and forth from excited to ground, And the rate at which it does that depends on the Rabi frequency. The Rabi frequency is proportional to the strength of the interaction. It is proportional to the amplitude, which in this case, in the spin case, was proportional to the magnitude of the transverse field. Okay? That is the strength at which it processes from down to up. Yeah.
So I hope I don't take up too much time, but I've not, sometimes with these Hamiltonians we have both the, the absorption and the emission parts of it. And so like if I had something that started in the excited state and interacted with the field with omega, it can cause it to drop.
Indeed it will.
And so, I mean,
that's called stimulated emission.
Like a laser? Or?
Yeah.
So, I mean, and I know we're not talking about photons, but like one will interact and then two will go off together or something like that, or?
Yeah, I mean, so this is, of course, there is a lot of subtlety here, Zeke, that we really don't have time to talk about. I'll mention this a little bit. The notions that you hear about stimulated emission, about a photon comes in and then two come out, these are very kind of, there's a billiard ball, there's one and then there's two. And that's a baby picture of what's going on. This is quantum coherent dynamics. And it's different. We're going to make a connection, I hope, we'll see where we get today, to the notion of what sort of, the picture of spontaneous and stimulated emission is more a rate equation picture, where we have populations. It's here and then it's there, and then it's here and then it's there. It happens at some rate. In this case, what's happening is there are, as we said, if we looked at this picture, as I went from here to here, well, I'm in a coherent superposition of spin up and spin down. And in fact, if I started here and I went here, I'm also in a coherent. So I'm sort of halfway in between the photon being emitted and not emitted. It's in a coherent, this is why I emphasize that I have this underlined twice.
Yeah.
That this is coherent.
It's hard to drop that picture that...
It is, and how we get from this picture to the one that, oh, there's one photon, then two come out, that's a very subtle business. We'll talk a little bit about that, hopefully at the end of this lecture, okay? But it is important to understand that when we're talking about us driving the system with one frequency, and if they have just two well-defined energy levels, then this is just coherent spin rotation dynamics. And what's going on, I mean, the photons are going in and out of the field, they're being absorbed and re-emitted at the field. This would only be really true when I have an uncertain number of photons, a coherent state that's not a Fock state with a definite number of photons. If I drove the system with a Fock state, it wouldn't look like this.
Okay.
So there's quantum optics there. And maybe next semester, I'm teaching that course, we'll talk about that. But thanks for bringing that up, because it is important to connect these different pictures. I don't mind just taking the time to discuss that, it's important. So yeah, just to complete that thought just a little bit more, is that this is the way in which one manipulates superpositions in modern quantum technologies. If one wants to create a superposition, that's how you do it. You have whatever your levels are. They could be two states of a superconducting circuit with persistent currents that represent well-defined quantum states of the circuit. They could represent two states of a trapped ion or a quantum dot. Whatever it is, if they have well-defined energy levels and I can drive them, if I do that in such a way I know what the effective Rabi frequency is, then if I drive it for a time such that omega t is pi over 2, I make a superposition. I can make any superposition. In fact, another thing to say about this is, well, we rotated this around the x-axis. That was just a choice. In principle, I could have rotated this around any axis by, for example, in this case, putting on a phase, right? So that means at time t equals 0, I might be rotating around, instead of this, I rotate around that axis, and then I can create any superposition. And I could do first rotate around one axis and then shift the phase of my oscillator and then rotate around a different axis. Of course, all of this is very dependent on my ability to have very well-defined oscillators with very well-defined frequencies and very well-defined phase control between them. All right, so let's see. A number of things to say here. Firstly, I wrote down that Hamiltonian by fiat. I just said, let's consider the case where I have an absorption term and an emission term. And we said the absorption term we saw from Fermi's golden rule was dominated, we saw linear resonance by the positive frequency component and emission by the negative frequency component. And then we saw that that corresponded to the rotating magnetic field. We rewrote it as a magnetic field. But let's consider the following problem. Suppose my B perp, for example, let's say it only oscillates along the x-axis. Okay, let's say we had such a thing. Okay, so I have my problem here from the point of view of the spin. Here's my B parallel. And now I have just a transverse magnetic field that's oscillating back and forth along the x-axis. It's not rotating. Okay? So, the Hamiltonian, if I go back to what we had, will look like let me call, so my Rabi frequency here is that, the x. All right? So that's my Hamiltonian now, slightly different from the form we had there. Let's see how it's different. So sigma x is what? Sigma x is equal to sigma plus sigma minus. Okay. Now cosine is e to the plus I, or e to the minus I omega t plus e to the plus I omega t. Right? So, what's going on here? Well, what you see here, so now let me write this out. This is going to be equal to sigma plus e to the minus I omega t plus sigma minus e to the plus I omega t plus sigma plus e to the plus I omega t plus that. So now I have, in contrast to what we had before, I have these other terms, right? These terms have the opposite signs, right? So this is related from the point of view of looking at this from the quantum levels, a situation where sigma plus is a term that's driving v to the plus I omega t. And sigma minus is driving with e to the minus I omega t. So what are those terms? And why didn't I include them before? Well, this we have to go back to one of our previous lectures to think about why we associated the thing that went like e to the minus I omega t with absorption, and the thing that went like e to the plus I omega t with emission. For that, let me go to the interaction picture now, okay? Because that's where we kind of saw. So in the interaction picture, so this is my H int. The sigma z is not my int, that's my H0. Put it in there, but it's not. The key is what's going on. Think about this one in view of what we saw when we were going in the interaction picture. So in the interaction Hamiltonian in the interaction picture, right, that's this. Is equal to, well, remind you of that, okay? So this is then equal to sigma plus e to the minus I omega naught t plus sigma minus e to the plus I omega minus omega naught. What's the other? Yeah, that's right. Yeah, good. And then I have this. Okay? So, what we see in this, the important point to notice, is that these terms have resonance. And these times are anti-resonant. In other words, when we did the perturbation theory, and we looked at the first order perturbation, we looked at the integral of this, and we ended up with energy denominators. Things that went like 1 over these exponents. And so when omega is close to omega naught, that was a big effect. That was a resonant effect. And so that's why we said, when we did this in the first place, We said these are the terms that we want to associate with absorptions, the ones that were like either the minus I omega t, and these are the things that said we had to do with simulated emission, because they are the resonant effects. Okay. So, so we neglect this under certain approximations. This is negligible under certain approximations. What approximation? Well, let's take a look at this again from the point of view of our gyroscope picture. Okay, so let's come back over here, and we were thinking about this. Remember what we had before is this guy precessed around this at omega naught, right? And now we have this guy oscillating back and forth at frequency omega. Now we can think about this in the following way. We can break up something that's oscillating along the x-axis. Let me draw the xy plane here, so I don't have to draw perspective. Okay, that's a different plane. This is the xz plane. Now only the xy plane. All right. This is a linear combination of something rotating clockwise and something rotating counterclockwise. Right? Any linear oscillation is a superposition of right and left circular. Right? So x is x, or x cos omega t, if you like, is equal to x cos omega t plus y sine omega t a half of that and a half of that. Right? So linear oscillation is a sum of two circular oscillations. So this oscillating field I can think about as a linear combination of something going around this way and something going around that way. So now let's think about the effect of the torque on this magnetic moment associated with the co-rotating and the counter-rotating fields. So let's think about that. Suppose the thing that we said that was co-rotating with this precession, the torque around that co-rotating will sort of add up because it's going in the same direction. While the guy that's going the other way is going to give it a little bit of jiggle around, but it's not going to add up because it's oscillating completely out of phase with this. So if, under the case that when omega minus omega naught, the magnitude of that is much, much, much smaller than omega, the counter-rotating term is negligible. It's not exactly true. There's another approximation. And this goes back to a point I made but I never used, which is that I'm assuming that the Rabi frequency is much, much smaller than omega. Because otherwise, there's a huge torque, and it doesn't really matter whether I have a co-rotating or a counter-rotating term. It's going to add up. So under the conditions, when the detuning and the Rabi frequency are much, much smaller than the resonance frequency, then I can neglect the counter-rotating terms. And this is known as the rotating wave approximation. It's, a name that goes back to magnetic spin resonance, where I thought about have a rotating wave. Okay? When I have the rotating wave approximation, actually, back to over 2 on this, and I can neglect that term, and then I get back to what I had before. So I can have that kind of linear oscillation and still make sense. Now, why is this important beyond magnetic spin resonance? Well, when I think about a different kind of two-level system, we'll see that the only way we could ever really get this kind of Hamiltonian is in the rotating wave approximation. For example, let's talk about, I guess before I do that, yeah, okay. Let's say that I have, let's talk now about the application of this to absorption, emission of a laser field by an atom. Okay. So let's say I have some atomic system, and let's say that there's, for example, a ground state. And I want to absorb this to some excited state. So there's a Bohr energy associated with that. That's like our omega naught. Okay. This is like our spin down, it's like our spin up. Now we're going to drive that with a laser that has that is very well-defined frequency, omega naught. Very close to resonance in the sense that the tuning delta is tiny compared to any other excited state. Okay? Then this is what's called a two-level atom. All right. Now, so my Hamiltonian in that case is equal to the H0 for the two-level atom. I can take the energy, zero energy, right in the middle there, just like before, where sigma z is equal to so this is like my spin up, and this is like my spin down. This has nothing to do with the spin of the electron. Nothing. It's just a label. Okay. This could be the 1s, 1/2 of hydrogen, and thus the 2p3 halves of hydrogen. Okay. With some hyperfine labels to make two very specific energy levels. Right? Everyone clear on that? That's H0, right? Because H0 in this case would then be, excited state energy. What is the ground state energy? Anyway, it's clear. Okay. All right, and H int. Well, let's see. What are we going to let's maybe take a little digression on H int, since where we are in the lecture, I'll do this now. Well, let's go back. Let's think about for a moment what we said. If we had wanted to talk about charges interacting with electromagnetic fields, that's what we did at the beginning of the semester. Let's talk about that. Let's do a little aside. Okay, so we wrote down in that case the Hamiltonian as that's how we wrote down the Hamiltonian involving the potentials, the vector potential and the scalar potential. And what we did at the beginning of this semester, we looked at the case of static fields. That's how we started. Particularly, we were interested when we had like static magnetic fields, and we looked at the Harmonic-Bohm effect and all those goodies. Now we're talking about electromagnetic radiation. Okay? So in electrodynamics, generally speaking, the electric field in the problem is given by the gradient of the scalar potential, but it's also dependent on the vector potential. Right? Everyone knows that from me then. And of course, the magnetic field is always just a curl of A. If I do a gauge transformation, so if there's some gauge function, now the gauge function can be a function of position and time. I can allow that. And under a gauge transformation, as before, we can change the vector potential by adding to it the gradient of any gauge potential, and that will in no way change the magnetic field. But we also simultaneously have to change the scalar potential through the time derivative. If I make these two transformations on the potential, then the electric field is unchanged and the magnetic field is unchanged. Question?
Well, I mean, in the end, we proved that relationship of the momentum in the field by making the Coulomb gauge choice. But then we can just keep changing the gauge over and over and over again.
Well, we haven't yet made any gauge choice here.
Well,
this is general. For any gauge, this is true.
Okay.
This is not in the Coulomb gauge. This is not in the Lorentz gauge. This is always the case.
It must have made the math easier for us to have chosen that gauge, probably.
Right.
Yeah.
So I'm about to do that.
Oh, okay.
Right. So. If I'm talking about, see, when we talk about electromagnetic fields, when we're talking about radiation, there's, if you remember from your studies of that, there's the near field, the intermediate zone, and the radiation zone, right? In the radiation zone, the fields are transverse. Okay? If there's no charges in the radiation zone. And so it's convenient in that case to start in the Coulomb gauge. where we start with a choice such that we fix the vector potential of zero divergence. So that's a choice of gauge. We can always do that, okay? And in that case, the part of the radiation electric field is just equal to this, which we typically call the transverse field. Okay, so the part that's the gradient of the scalar potential is related to the near field part of the electric field, and this is related to radiation in that case. Okay. All right. This is what's called the minimal coupling Hamiltonian. However, it is not the convenient form of the Hamiltonian when we're talking about non-relativistic dynamics, for reasons that I'll explain right now. Okay. When the dynamics of charges are non-relativistic, that is to say, if I have some charge distribution and it's moving around, if the time it takes light to travel across this distribution is absolutely tiny compared to the time scale over which the charges change, that's equivalent to saying that if I think about the charges oscillating with some frequency, omega, so this goes like 1 over omega, this is saying that omega over c wait, do I have this upside down? Hold on a second. No, that's right. Much less than, right? Which is another way of saying that this, of course, is proportional to 1 over lambda. Which is to say that lambda is huge compared. When that is the case, then we can make the multipole expansion. Now, I'm not sure if this is something that you've studied yet in 511, but the interaction of an electromagnetic field with a charge distribution can be expanded in a convergent multipole expansion when this is true. If the wavelength is very big compared to the charge distribution, which is equivalent to saying that the time it takes light to travel across the sample is tiny compared to the time it takes the charges, then I can make a multipole expansion. And we want to do that. For example, if we have a laser, the laser has about a half a micron of wavelength for optical fields, whereas the atom is an angstrom. So it will dominantly interact with the lowest non-vanishing multipole moment. Okay, so in order to make that multipole expansion, we want to make another gauge transformation. Okay, and so this is known as the power Zinu-Woolley transformation. So I'm going to define a new gauge function, which is equal to this minus that. I mean, dotted into that. Okay? Still transverse. So now the gradient of chi is equal to, I have to take the gradient of this thing. And then go through, you know, your epsilon, ijk's, or whatever, and you get the following. Plus the terms that depend on the divergence of A, but the divergence of A is 0. And minus 1 over C d chi dt is equal to minus R dotted into which is minus R dotted into E. And this is D. So I'd make my gauge transformation in this problem. A goes to A plus the gradient of the gauge function, and the scalar potential goes to the old scalar potential minus 1 over C d A dt. I mean, d chi dt, pardon me. And I plug this in to the minimal coupling countercurrent. And what do I get? Well, I add this. This is going to subtract off the vector potential, which was, and then leave me with this. So it's going to look like, H now looks like 1 over 2 m P plus E over C B cross R squared minus E R dotted into the electric field minus whatever the old scalar potential was. Sorry, yes, it's plus. This guy is plus. All right, so the nice thing about the power zero Woolley transformation is everything now is expressed in terms of E and D. Instead of A and phi. Okay? This is the electric field at the position of the electron, and similarly for this. Now, we studied this when we looked at the case where we had a static constant magnetic field, and when we rewrote this, we saw we had paramagnetic and diamagnetic terms. The diamagnetic term is completely negligible when we're driving this tiny atom. It's only the paramagnetic term that matters. And what we saw was that this was equal to where mu is equal to E over 2 mc L, and D is equal to the charge of the electron at this position. Okay? Of course, we can also we should add in, if this is an electron, we should really add in spin as well. That's not, that in the Pauli interaction we went back, we really should put that in as well. All right. Now, this is at the position of the electron. I have not yet made the multipole expansion, even though it looks like I did. I didn't make any approximation yet at all. I just did that. So, what am I going to do in this situation? Well, here's my atom, here's the proton, here's the electron cloud. The size of my atom is about A naught. And then I have my electromagnetic field, which has some huge wavelength compared to that. Okay? So now, under the multipole approximation, what it's saying is that the position of the electron relative to the center of mass is tiny compared to this extent. In which case, I can make, if I'm making the multipole expansion, I take the electric field and expand it around the center of mass. This is at position R. That's the center of mass of the atom, position of the atom, plus R minus R dotted into the gradient of the electric field evaluated as R plus dot dot dot. And similarly for the magnetic field. All right, so what that, under this approximation, my Hamiltonian is equal to p squared over 2m minus the electric dipole operator of the atom dotted into the electric field at the center of mass of the atom. Then I have a term that looks like this. Plus E R let's see. Dotted into the gradient by E. Evaluated R. Then I have terms that are like this, and I'm not going to expand beyond that. Yeah.
Isn't that term in the Taylor series a scalar, the second one? Shouldn't it be a vector?
No, it's a, this is an E vector. So this is,
Oh,
It's a directional gradient.
yeah. So, but what we see here is the following. This term is related to the electric dipole moment of the atom dotted into the electric field at the position center of mass of the atom. This term is related in some way to the quadrupole moment in ways that we'll we'll explore more. There'll be hexadecipoles and so forth the poles. Of course, this is the magnetic dipole. And what we know from electromagnetic theory is that when lambda is much, much smaller than the size of the atom, the electric dipole moment dominates. Okay, that's maybe not something you've seen yet, but the strength of this interaction is dominated by the electric dipole moment. What we'll see is that the quadrupole, electric quadrupole and magnetic dipole are of the same order. It's because magnetic effects are down from electric effects relativistically. Remember, we made the non-relativistic approximation. We assumed that the speed of the electrons was small compared to the speed of light. This is one power down from this, and this is already one power down from this. So these guys are of the same order. The bottom line of all of this is that when we're talking about non-relativistic motion of charges and atoms, we often take our interaction Hamiltonian to be this, rather than P dot A, which you'll see all the time in quantum field theory. And this is known as the electric dipole approximation. So, let's go back to the backboard. We can now write down H int. H int is minus D dotted into the electric field at the position of the atom. Okay. And my electric field, let's take it to be a plane wave. Like, we'll approximate our laser beam as a plane wave with some polarization direction, some amplitude, and it's a wave. Okay. So this is equal to now, as any oscillating field, it's some amount of even plus I omega t and some amount of even minus I omega t. Okay, so that's my field. Now, we said that when we're tuned close to the resonance, we can restrict all the dynamics to this two-dimensional Hilbert space, which means that I can expand this in a complete set, but I don't have to sum over all of my resolution of the identity is only going to account for these two states. I don't have to include, I mean, if I write a resolution of the identity and shove it in, I really should sum over all states, bound, unbound. But when I'm tuned near resonance, two levels, the whole story. Everything else doesn't dominate, doesn't matter. Okay? So let's, where should we take it? Back to the front board. Right, so my interaction Hamiltonian thus is equal to minus G, G, D, G, G, plus E, E, D, E, E, plus G, G, D, E, E, plus E, E, D, G, G. Dotted into okay. This is D dot E. All right, now what? Well, these E and G are supposed to be energy levels of the atom. They are defined by a good quantum number L. Right? The 1s or the 2p or the 3d or the 5h. Right? Those are always, L is always a good quantum number. Which means the eigenstates of the energy levels of the atom are eigenstates of parity. Which means that since D, as written over somewhere here, is an odd parity operator, as we know, and I'm sure you all did this properly on your exam, there are no diagonal elements of the dipole operator with states that have the same parity. So these are gone for an atom. Okay? All right, so let's rewrite our interaction now. What we thus have is our interaction Hamiltonian is equal to minus what I'll call DEG plus BGE dotted into the polarization, the amplitude over 2, is IK dot R. This is omega laser. Okay? This is the wave vector of the laser. All right, what do we see? Well, in our two-level approximation, this is what we call sigma plus, and this is what we call sigma minus. Right? And here our DEG is the matrix element that looks like that. And that's the conjugate of the other. Now, I can always choose the phase of the wave function. I'm going to choose this to be real. I can always do that through appropriate choice of the overall phase of the wave function. And so this then has the following form. I'm also, for the moment, let's take, and we'll come back to this, take the atom at the origin. Doesn't matter, I'll come back to that in a moment. Let's just conclude this. What do I see? This has the following form. Sigma plus sigma minus where h bar omega is minus dEg dotted into the field. Okay, so the Rabi frequency for this problem is the frequency associated with the energy scale of the interaction. That's always the case. In that case, it's the interaction, before we had a magnetic dipole moment interacting with the magnetic field. Here it's an electric dipole moment interacting with the electric field. So that's the Rabi frequency. Okay? We have, as you see here, resonant and anti-resonant terms, co-rotating and counter-rotating terms in the pseudo-spin picture. So in the rotating wave approximation, when the detuning is small compared to the oscillation frequency, and when the Rabi frequency is small, so in the rotating wave approximation, this is approximately equal to exactly the spin resonance Hamiltonian we wrote down before. Exactly. And if the atom weren't at the origin, what would that change? Well, that would mean we would rotate around the x-axis, we rotate around a different axis, depending on the phase, the local phase, because this was like the phase that we put when we had the torque vector. If we said if we just changed the phase of the cosine or the sine, we would rotate around a different axis. So, to the degree to which the atom's fixed, we just call that phase the reference phase. So just to conclude, let me just come back to the backboard here. What this means is the following. If I have a resonance, so this is the ground state of the atom, this is some excited state, and I tune my laser to this. In fact, if I tune it exactly on resonance, I will start in the ground state, and then after a pi time later, I'll be in the excited state. And then 2 pi time later, I'm back in ground state. And I will flop back and forth. That's called Rabi, that's Rabi flopping or Rabi oscillations. And in fact, if I stop at when omega t is omega being capital omega, when this is pi over 2, then I'm in a superposition of those. And I can make any superposition I like through a particular choice of phase, amplitude, and time. Now, there's one thing that a very important thing that I neglected, which is, of course, we also know that typically the excited state is metastable. It will decay. And we're going to talk about that next lecture, due to spontaneous emission. So this picture of Rabi oscillation only makes sense if the Rabi frequency is much, 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 much bigger than the rate of decay. That's to say, the Rabi period has to be short compared to the lifetime of the atom. Otherwise, it gets there and it decays and it loses coherence. So this is an example of an incoherent process. This is an irreversible, dissipative process. That's a complicated business, and we're not going to have time to really get into the whole business of open quantum systems, but we kind of touched on the beginning of the lecture when we talked about decoherence in 521 and open quantum systems. You can go back, I have the video record, you can see it. And in that case, we don't have coherent Rabi observations. We have something that's irreversible. It's a complicated business. We'll talk a little bit more about that next time. All right, have a great break, everybody.